distinguished professors, doctoral students, bachelor's and master's students, all attendees, allow me to present this work to you under the title Solar Thermal Energy to Drive Ejector Vac Systems, where this scientific work was submitted by the Dr. Ghodbane and his colleague. This scientific presentation will be presented according to this work plan. 1. Abstract. 2. Presentation of ejector air conditioning subsystem. 3. Presentation of parabolic trough collector subsystem. 4. Presentation and discuss of results. 5. Conclusions. Abstract. This scientific work aims to show factors that have a direct impact on solar air conditioners that use the ejector as an alternative to the compressor in order to reduce electricity consumption in the refrigeration field. The weather data of Blida region were selected as the main data for conducting this study. Parabolic trough solar collector has been made as a solar device to provide the thermal energy needed for the generator. All the mathematical equations that dominate the system have been analyzed and then numerically simplified using e-software. The optical efficiency of the studied solar collector was 66.50%, while its maximum value of thermal efficiency was only 61%. As for the machine, solar thermal ratio reached 0.41. Serious exploitation of this technology will allow solving the problem of high consumption of electricity in the hot seasons, and also allows the preservation of the environment by using water R718 as a refrigerant. Ejector air conditioning subsystem. Figure 1. Illustrative schematization of a typical ejector. Figure 2. Operating cycle of an ejector air conditioner. Parabolic trough collector subsystem. Figure 3. The energy balance at the receiver tube. Table 1. Geometrical parameters of the studied solar collector. Table 2. Optical parameters of the studied. Discuss results. Ejector air conditioning subsystem performance. PTC thermal efficiency. Machine solar thermal ratio. Figure 4. Solar ejector air conditioning system for balance analysis. Figure 5. Direct normal irradiance assessment. Table 3. Service operating conditions of the studied machine. Figure 6. Temperatures assessment, receiver tube, heat transfer fluid and glass tube. Figure 7. Estimating the coefficient of total thermal loss for the used solar collector. Table 4. Dimensions of DT and DM under critical conditions. Table 5. The drive ratio and the performance of the ejector cooling subsystem with a cooling load of 18 kW. Figure 8. Assessment of system thermal ratio. Conclusions. This work has allowed us to acquire very important knowledge about ejector solar air conditioning machines. According to this study, the performance of the air conditioning subsystem (CAPAC) is very sensitive to changes in condenser temperature (TC). So to increase the performance of the machine, it is necessary to increase the temperatures of the hot sources (TG and TE). On the other hand, it is found that the parabolic trough concentrator is effective to operate this machine, even if it has a good thermal efficiency. Where in this study the PTC thermal efficiency reached 61%, while the solar thermal ratio (STR) of air conditioning system in critical mode was 0.41. In addition, this technique can be exploited in the Algerian desert, where the fossil energies are extracted and exploited. This technology will reduce the consumption of electricity in these institutions in large proportions. In the future, we will try to experiment with this system, and we will work to improve the operational conditions of this type of systems. Thank you for your attention.